To ask some more technical questions. How do you make your rocket engine? What fuel and oxidizer do you use?
So for the engine itself, most of it is 3D printed in Inconel, and is 3D printed by one of our main sponsors, Materialize. The propellants that we use as fuel, we use ethanol, and as oxidizer, we use liquid oxygen that, as you might know, is cryogenic. So we need to deal with those cryogenic temperatures. And as for these specs, we aim at, we have theoretically a thrust up to around 15 kilonewtons.
How do you design the engine?
How we design it? Well, so the actual combustion chamber itself, we use CATIA, which is a 3D modeling program, and we also use the online version of that, which means that we can actually share our designs between our members. So we first designed it in 3D. Of course, before that, you have a phase where you look at the requirements, like what do you want the rocket engine to do exactly, how much thrust do you want, and then from that, you already have a lot of things that you know about it, like how big does it need to be to produce that thrust? How hot will it get? So what kind of cooling will you need? So it's a whole design process that took, a large part of last year. So quite intense. And then, as I said, we model it in CATIA, and then we send it off to be printed.
Yeah, we also use COMSOL as a simulation model for thermal flows.
And how do you cool down your engine?
So we have two methods of cooling the engine. The first one is regenerative cooling. So basically, the fuel of the engine is used to cool the engine as it runs. So the ethanol, instead of entering the engine through the injector manifold, so let's say the logical way from or the top to the bottom, it will actually go first all the way to the nozzle. It will enter the engine through the nozzle, and there's many channels, really small channels that run along the walls of the chamber, and the ethanol kind of is pushed through those channels back up into the injector, and then injected into the combustion chamber, where it mixes with the LOX. So basically running cool ethanol through the channels, it's one of our methods. The other method is film cooling. So basically at the intersection between the nozzle and the chamber, we have a film cooling ring that injects part of the ethanol into the nozzle. And this ethanol creates a barrier that protects the nozzle from the high temperatures of the combustion.
Do you have any ideas to use cold gas thrusters?
Well, this is part of the rocket design. That is something that we haven't really gotten into yet. So once we have this engine done, we want to either start a new project that maybe builds a rocket around it, or continue this project to do that. So it's not something that we ourselves have been actively working on. It seems like we'll definitely need some kind of rotation counterbalancing, because of course the thrust vector control can control our pitch and our yaw, but not our roll. But actually, one of our previous projects, Stratos 4, already had a roll control department that exclusively was just there to look into this issue. Carmen, do you have any more info on that?
Yeah, I can give a bit more. So basically, one of the reasons that was was found for the failure of the launch of Stratos 3 was the pitch roll coupling. So basically, coupling of the frequencies, and the method that was found to prevent this was by controlling the roll of the rocket. And for that, a roll control team was formed. And this roll control team of the Stratos 4 worked for about 2 years on developing these thrusters. And they've never gotten to actually test them because the Stratos 4 rocket has never flown. So most likely in the future, if the next Stratos rocket with the Sparrow engine were to fly, and the legacy, let's say, of that roll control team will be also implemented in this new rocket. So it is not something we're working on currently, but it is most likely something that the next team that designs the rocket around this engine will have to implement.
Will you use thrust vectoring?
Yes. So as I said, we are developing a thrust vector control system. Currently, it's more of a demonstration to show that we can actually do it. Thrust vector control, of course, is pretty complicated, especially because, well, when a rocket is actually flying, you need very high, so very low latency and very high reaction speeds, of course, of the actuators that move your engine around. So it's a coding challenge. It's also a challenge of getting the right equipment, of course. It's very difficult to get actuators that are precise enough, that are quick enough, and light enough at the same time. But yeah, currently they're developing the simulation models of how we can actually control our engine in real time based on the way that it is moving. So that's definitely in the works, and it is also definitely one of the key things that we said at the beginning, is that we're going to be a regeneratively cooled thrust vector controlled liquid rocket engine, because there is just no way to get our safety range small enough to be able to guide ourselves into orbit. And even right at the beginning of the flight, with the instabilities that you get into a rocket, there is just no way to do that for us without incorporating that thrust vector control. So that's something that's been part of our project from the beginning.
How do you design your rocket?
I think, well, Nathaniel explained before, so we follow always a structured approach, going from a mission to requirements to designing subsystems around those requirements, and then do some validation testing, and then finally testing the rocket at the end. Currently, we are in the engine development phase, not yet rockets. And in the society, we are the team that is working the most on liquid rocket engines. We also have teams that are working on solid engines, which are usually the engines that the smaller rockets of the society use. And Stratos in the past had a hybrid engine as well. So we kind of have experience with the most common types of rocket engines.
Yeah, and if I can add to that, we also do a lot of research, for example, into new types of propellants. So in the past, for solid rocket engines, we've mainly used rocket candy, which is sorbitol. But we're right now looking into more efficient ways to power our rockets. We're also getting into hybrid engines again after Stratos, and even some more green solutions, let's put it that way, to power rocket engines. So there's really a lot of research in DARE is centered around propulsion. And we're kind of the flag carrier of that with our liquid rocket engine.
Do you use trapezoid fins, and if yes, why, and if no, why not?
Currently, we as Project Sparrow are only working on the engine, so we cannot really say what we are using or not using because there is no rocket yet. But there are many other teams in there that are developing rockets right now. So if you're interested, we can also maybe have them come here for a small interview as well. For example, the Europe team or something, and they can explain the actual rocket design. Because currently we're just in the engine, a really cool engine, but the engine phase.
On your website, it seems that the Stratos 4 has trapezoid fins, I think.
I'm not quite sure why they, in the end, went with that design. But what I can tell you is that the simulations were extensive, as they are for all our rockets. Stratos 4 had a specific simulations department that did safety range simulations, aerodynamic simulations, flight path simulations. look into what the most efficient design is, especially for things like fins that are obviously crucial and a quite fragile part of your rocket. So I'm sure there was a good reason for why they went with it in the end. I wouldn't be able to tell you myself why.
I think they went with the trapezoid fins because they're more aerodynamic. Because like if you have a triangular fin, then it has some thickness, and then when it goes through the air behind, it leaves a bit of low pressure, so that's less aerodynamic. So I think they went with trapezoid fins so that they are more aerodynamic. Instead,
yeah, that's probably it.
yes. Instead, for electronics, do you have like a PCB, or do you have another type of board? What do you use?
So I think for flight computers, we usually have PCBs and like custom electronics that are designed by our electronics team, and yeah, produced for us. As for the software, currently we use mostly LabVIEW, which is a control software that also has a graphical interface. Although we're also trying to move towards the direction of Python, since Python is one of the most, well, it is a language that is growing a lot. Also at the faculty, it is the language that you get taught how to program in. So it would make sense if we manage to do everything we can do with that language. And yeah, in terms of sensors right now for our own engine, we mostly are relying right now, or our control department is mostly working on data acquisition. So we gather data in real time, and we are able to, well, to see it and to make decisions during testing based on that data.
Oof. Yeah, well, it's quite a lot of facets to it, of course. Right now, as Carmen said, the focus is on gathering as much data as possible during the test. So, of course, because it's still a ground system, we still have a direct cable link to our engine through our flight computer, pretty much. So all our valves are directly actuated. We can gather data straight from our engine with thermocouples and pressure sensors. But of course, yeah, at some point we will have to move towards a flight system where we have a flight computer, which means that we will not be able to actuate it through a cable, but we'll have to send commands and have it work on its own. I think last year's team worked on a real-time Linux kernel for that. So we'd have a latency below 10 milliseconds. So we can actually, basically send commands and have our direction of our thrust vector control change every 10 milliseconds, which is quite fast, of course. So that's what they were working on for that. And yeah, any further than that, I don't think we've gotten in terms of a flight system. As I said, we've been developing the models that will actually allow the thrust vector control system to will know which way to pivot based on what the rocket is doing and which way it's pointing. But that's also still very much in development.
Do you use air brakes, or do you have plans to use aerodynamic surfaces to decrease or increase drag?
There is a very, very large team at DARE that is called the Parachute Research Group, PRG, and they've done a lot of research into different types of recovery systems. So I'm sure they have looked into this, and probably they're willing to explain a bit more of their research. I know they've published so many papers. So yeah, again, we are still in the rocket part, but there's a lot of experience in there on recovery systems.
Exactly. PRG is a very skilled team, and they've already developed a recovery system for a large rocket. I mean, Stratos 4 is over 8 meters, I think, if I'm correct, and they developed a recovery system for that. So the parachute, well, if it were to come to that, and we were to put Firebolt on a rocket for DARE, then they would also definitely be involved in the recovery system there. I'm not quite sure about like specific aerodynamic surfaces. I don't think we have a lot of experience with that in the society, but we've mostly worked with parachutes so far, and it's something we're able to very well test in the wind tunnels that, for example, are available at the university.